Hello, everyone, and welcome to our plastic recycling sorting machine design review. Continuing with our final concepts, we generated detailed configuration designs, and several parametric designs for our recycling plastic sorter. The following report takes economic, social, and environmental factors into consideration. The main modules of the sorting machine include the frame, the garbage chute, the singulator, the sensing ring, the conveyor belt, and the sorting paddles. This is our final 3D model of the sorting machine. The EPA estimates around 3,090 tons of plastic is recycled each year. The smallest compared this is small compared to the 35,680 tons of plastic generated in 2018 alone. This means about 9% of the plastic generated is actually recycled. After doing research and talking to various startup companies, we concluded that buyers to in order for the plastic buyers to buy back the recycled material, the batch needs to be over 96% pure. Sorting by type would allow a greater fraction of the waste stream to be reused. The challenges are that the items in the stream are different size, color, and shape. Our problem is to design a recycling machine that uses a combination of NIR detection and image processing to increase batch purity that can be used in large metropolitan areas.
This is our design specification matrix. It's a bit small, so I'll explain the important functions and design specifications in the next slide. So in this iteration of the DSM, we added any extra engineering characteristics that we came up with in column 3, and we filled out column 4. So the important functions of our recycled plastic sorter are the identification of plastics, the sorting of plastics, and the transportation of plastics. For the identification of plastics, we need this function to be accurate, which we measured by failure or error rate. We specified that we wanted 5 errors, or less than 5 errors in every 1,000 items sorted. The subsystem related to this function is the sensor ring. For sorting of plastics, we need this function to be fast. We can measure this by sorting speed. We specify that we want at least 20 items sorted per minute. And the subsystem related to this function is the sorting system. And for the transportation of plastics, we need this function to be automated. We can measure this by the level of automation. We want at least level 3 automation based on the 6 levels of automation. So here is a list of our overall product functions. They can be found in column 2 of our design specification matrix. These functions are addressed based on the coming product architectural layout. The following systems are required for the final modular layout of our product. Each of these subsystems are integrated together to make up the overall machine. They work cooperatively to achieve each of the aforementioned product functions. The subsystems presented in our final concept are an inner frame, external shell, garbage chute, singulator, sensor ring, conveyor belt, sorting mechanism, and storage units.
The inner frame provides support for the exterior shell as well as gives a backbone to the internal system. This support structure is needed to accomplish the product function associated with design factor of safety, and able to fit into limited spaces, and also increase part longevity. The inner frame directly interfaces with the exterior shell as well as provides support for the hanging sorting system and the sorting ring. It must be able to support their weight reliability. The external shell provides protection to all the internal mechanisms and increased longevity for the parts by not having them exposed to exterior hazards. The external shell provides an entry point for the storage area as well as the garbage chute. It also provides a location for the central module that controls the entire machine.
The garbage chute is the entry point into the overall system. It is related to the minimal human intervention product function, as the user only needs to insert their waste through the front, while the system takes care of the remaining sorting tasks. The garbage chute interfaces with the singulator by transporting the materials into the singulator so they can all be oriented in the same direction.
The singulator orients all the materials in the same direction to optimize the sorting speed and sorting efficiency of the system. This in turn provides a direct import for recyclables and requires no pre-sorting beforehand. It also separates the stream plastic and allows one item through at a time. The singulator interfaces with the sensor ring and conveyor system to sort and transport the materials efficiently.
The sensor ring's job is to identify the materials before it enters the sorting system. This is done using the arrangement of sensors demonstrated above. 3 NIR sensors are utilized directly above the machine to use infrared spectroscopy to identify the material. 3 cameras are facing outward to identify the numerical code on the plastic in order to increase identification accuracy. 2 cameras are facing inward to look for the numerical code as it passes through the ring. In our concept selection, we mentioned a camera underneath the conveyor belt. However, this was not practical to implement because we used a standardized conveyor.
The conveyor system transports the materials along the conveyor belt so they are lined up with their associated storage bins and sorted using the sorting paddle mechanism. The conveyor belt speed is variable and can be turned for optimal performance. It also removes food waste and residue from the important bins by directing undesirable materials to the waste bin at the end of the belt. The conveyor system cooperates with the sensor ring, sorting mechanism, and storage to properly transport identified materials into their appropriate receptacles.
The sorting system is needed to properly direct each plastic system into their specific bins and decrease the identification error for the materials. The paddle interfaces with the conveyor belt and the sensoring to properly sort the plastics.
The storage area is needed to reduce space and allow for the designated sorting spaces for each of the plastic types after they're separated. It is also one of the few areas that require direct human maintenance and intervention. It directly interacts with the inner frame, outer shell, sorting paddles, and conveyor system to take the transported plastics and place them into their designated bins so they can be retrieved once they're full. As a group, we had settled on using a singulator as a primary means for orienting the plastic, but for transportation, we experimented with different methods, including an overhanging conveyor belt and a pneumatic chute. While both of these methods were viable, we decided to keep things simple and use a conveyor belt resting on the ground.
Continuing with the final concept we generated, we created detailed configuration designs for each subsystems. The subsystems will be introduced in the order of which the recycled plastic interact with our product. The door/chute serves several roles, the first being the point of entry for users to input plastic. The second is it acts as a chute onto the singulator. The first standard component is an aluminum hinge to attach the door to the exterior of the sorter. The second standard component is a zinc handle, which provides users with a non-slip grip to open the door to the sorter. The door will be a custom component. The shape and size need to meet specifications required for the singulator input. There were several potential materials: carbon steel, galvanized steel, plastics, fiberglass composite, and carbon fiber composites. The material selection process consisted of 7 different categories: function, environment, shape, aesthetic, manufacturing, cost, and sustainability. In the end, based on the selection criteria, stainless steel was chosen with the manufacturing process of sheet metal fabrication.
The next part in the chain is the singulator. The purpose of the singulator is to separate an incoming batch of plastic into a stream and only allow one item through from the stream at a time. It also reorients the plastic to most easily pass through the sensor ring. The singulator speed can be controlled by input from the sensor ring. There were a couple design choices to make for the singulator. The first was to select a drive motor. You can see our calculations here, and in the end we decided on a McMaster car motor with a 32 RPM free speed and a 400 inch-pound max torque. Our operating point is shown here on the graph, and it results in a singulator cone speed of 3.75 RPM, or 16 seconds per revolution. Another configuration design decision we had to make was the placement and orientation of the bearings required to support the singulator. There are 3 configurations we considered. In the end, we chose the last configuration because of its low cost and ease to implement. We then had to choose our bearings. The bearings we ended up using were Z99 R16 sealed bearings, which have a bore diameter of 1 inch, an outer diameter of 2 inches, and a thickness of 0.5 inches. We found that our load case only puts these bearings at less than 1% of their max rated load, so these bearings are actually highly overrated for our design. However, we still chose them because they would be able to slide right into the 1-inch shafts that also serve a structural purpose in our design. The first custom design component is the singulator cone. This is the rotating element in the design. It's a conical shape with an angle of 45 degrees and the diameter is set to be 5 feet. There's a hex interface in the center of the underside of the cone to drive the rotation. The second custom design component is the outer frame. It's primarily a structural element and supports the singulator cone, and the sidewalls also take part in the dragging action of the singulator. It has cutouts left in it to interface with the conveyor belt. We chose to perform material selection for the singulator and outer frame together because they have similar considerations in size. These were our material candidates. And this is the process that we used for selecting the material. In the end, we decided that the best material for this is stainless steel sheet, specifically 304 stainless steel in sheet metal form. It fits our requirement of anti-corrosiveness and structural strength. Knowing the material, we were able to determine how the cone will be manufactured. It will be comprised of a stainless steel shell formed by bending sheet metal at very shallow angles. It is then welded to other parts in the structure to finish the process. The outer frame will be a bit different. It will be rolled into shape as shown in this picture here. Similarly, the rolled pieces will then be welded to each other to form the final structure. Our last custom design component for the singulator is the inner frame. This acts as another support structure for the singulator and also provides shafts for the bearings to rest in. There's also a central bearing to constrain the drive shaft radially. We only had 2 potential materials for this as it had to be formed out of metal tubing. These materials were stainless steel and aluminum alloy. This was our material selection process. And again, the material we ended up deciding on was 304 stainless again, but this time in the form of hollow tubes. We can use these tubes to manufacture the structure out of the process of mitering and welding. The rods are cut and then filed to a shape that fits other rods, before finally being welded into place, as you can see in the picture here. This is a similar process as used by many other applications, such as bicycle frames and plumbing.
The sensor ring is designed to identify the object before it enters the sorting mechanism and sorting bins. It is composed of 7 different parts. The quantities of each part are listed above. 3 of these parts are standardized parts, including the NIR sensor used to identify the material using near-infrared spectroscopy and an 8-megapixel camera used to determine the material to identify the numerical code 1 through 7 on all the plastics. The last part is a plastic spacer used to give the arches rigidity. Using several different sensors, each sensor verifies the results with each other and meets our DSM requirements. 4 parts are custom designed in the sensor ring. The sensor arch is used to hold the sensing bracket in place so that the object can move underneath it. The forward camera mount holds the front-facing camera at a 45-degree angle at 3 locations. These are some of the potential materials considered for the part. The arch support bracket is designed to hold the ring to the conveyor using 8mm hardware. The sensor mount is designed to hold the sensor to the ring and keep it tangent to the ring. The following list of materials are potential materials that could be used to make this product. This is the process we use for selecting the material for the sensor arches. The main consideration factor was its shape. This is the process we use to selecting the materials for the brackets. Its main deciding factor was manufacturability, strength, and shape. We finally picked acrylic sheets for its ability to cut easily into its design shape, its lightweight, and low cost. We plan to use galvanized steel sheet for the brackets because of its corrosive resistance, strong and easily manufactured into its shape, and using a sheet metal press to form it to make the angles.
As a group, we opted to treat the conveyor system as its own standard component with custom component elements. The template conveyor belt we used was part number 5816K811, located on the McMaster-Carr website, and contains all the necessary components needed to assemble it. Since we chose to treat the conveyor system as a standard component, each of the specifications listed on the McMaster-Carr website are already predetermined. The key information to note is the width of the belt is about 12 inches or 0.3048 meters, but there is also a frame width of 17 inches and an overall width of 22 inches. The full length of the belt is approximately 7 feet long and contains an overall height of 34 to 38 inches. Additionally, the motor used in this conveyor belt is a 90-volt, totally enclosed non-ventilated motor that can output about 0.5 horsepower or 0.3729 kilowatts of power. The material is primarily galvanized steel for the support frame and conveyor bed, with the belt being made of aggregate PVC plastic. These are the graphics of the conveyor belt prior to being adjusted, a 3D CAD model and its respective drawing. It is important to note that given the dimensions of the overall machine, the conveyor belt we opted to use was both too short vertically as well as horizontally. We adjusted the 3D model to fit the dimensions of the whole project so it can interface with the sensor ring, singulator, and sorting paddle mechanism properly. Some key other points are that despite having to be altered, the overall function and requirements for the alterations have not changed. To properly integrate with the already produced conveyor component, any extensions to the belt will be made of PVC plastic, while lengthening the frame legs as well as the frame bed is made of galvanized steel. This excessive galvanized steel will be processed and manufactured using the galvanization process and metal fabrication. The resulting components will be longer legs, a longer belt, and a longer frame. In-depth material selection and manufacturing was not considered for this because the changes were completely based on the pre-existing component and the design has not changed from the original. These are the list of new specifications the ideal conveyor belt we were trying to achieve would have. For the most part, all of the specifications have not changed minus two important changes. The overall length increased from 7 feet to 11 feet, and the overall height has increased from between 34 to 38 inches to 42 to 46 inches. Much like the original conveyor belt, these are the 3D CAD model and drawings for the new conveyor belt after it had been altered to fit our design.
So here next is the sorting system. So this is the motor. The first standard component is the motor, specifically the 12-volt DC 107 RPM by C Technologies. It's sold on DigiKey. It has a max torque output of 0.08238 Newton meters, which is not powerful but sufficient for our product. The first custom design component is the sorting paddle. The paddle has to fit inside the inner frame, so we require the paddle to be a custom design component to fit within the confined space. These are the materials we considered. And here are the 7 criteria that we use to decide our material. So same as the singulator, we decide that the best material to make this component is stainless steel, specifically the 304 stainless steel. It fits our requirement of anti-corrosiveness, and it has the structural rigidity for our use case. So the material will be cut to spec by either a water cutter, a plasma cutter, or a laser cutter, depending on the manufacturer. The counterweight and the motor connection, which is the square and the circle section, will be welded on. And we learned that the welding stainless steel might be tricky sometimes, but for the size of our part, it shouldn't be a problem for our manufacturers. So the next custom design part is the brush and brush holder. It acts as a soft interface and transition between the paddle and the conveyor belt to prevent any damage to the expensive conveyor belt system. The brush on the paddle allows the paddle to reach flattened or not rounded plastic bottles. Because our paddle is custom designed, the paddle and the brush holder also has to be custom designed to fit our product. So here are some of the materials we considered. And these are the 7 criteria we consider for our material selection process. So we figured that using man-made materials such as polyesters and nylon will be better in both procuring the material and quality control for the brush head. The holder will be made from aluminum extrusion, which allowed some complex geometry at a reasonably cost. So ideally, we want to source a brush and brush holder from manufacturers such as Colnite that specialize in nano brush and holders that are usually used in escalators. We also did some parametric design to figure out the dimensions of the counterweight to determine the overall size and dimensions for the paddle. Calculation is done by hand first, then double checked with MATLAB. So this is the MATLAB code we use to verify. we conclude that the counterweight should be 70 millimeters in length to make the paddle balance. And with that length, we conclude that the paddle will be about 1.8 kilograms. With the way we can find the speed of the paddle when paired with our motor, we use the spec of the motors given by the manufacturer, the mass properties given by SolidWorks, and kinematics calculation to find the angular velocity of the paddle. So with tau equals I alpha V, and also omega squared equals with these two kinematic equations, we conclude that the angular velocity will be around 1.857 radians per second, which equals to about 0.3157 meters per second with our paddle length of 70 centimeters. With that speed, we conclude that the bottle will be launched at a speed about 15 meters per second.
So the length of the brush must be determined to provide an adequate amount of deflection to sweep the surface of the conveyor belt. In order to determine this length, a stack-up analysis was performed to determine the expected gap between the bottom of the paddle and the top of the conveyor belt. These were our results. In the end, we decided on choosing a brush length of 4.7 centimeters, which corresponds to 2 sigma. If the gap is larger than this, then the adjustability in the legs of the conveyor belt should help compensate for the extra gap.
The next subsection is the inner frame, which fits within our goal of fitting within the US standard parking space, which is dimensions of 2.5 meters by 5.5 meters. So the first standard component is the three-way corner bracket. The flat edges allow us to flush mount the outer panel on the rails and avoid any user or worker injury down the line. To construct the frame, we also need some brackets, and the following will be some of the brackets that we use. This is a T bracket. The next is a cross surface bracket, and we also use the flush T bracket. For our frame rail system, we use a M8 screws with various length depending on the location. So the only custom design components for the inner frame are the frame rail itself. These are some of the materials we considered. These are some considerations we made when deciding the materials, and we settled on using T-slot aluminum extrusion. We choose it mainly because of its simplicity and large catalog of readily available components such as hinges and mounts. While we understand that aluminum extrusion can be quite expensive compared to other frame materials, we believe that the benefits outweigh the drawbacks. The aluminum extrusion will be manufactured in a manner similar to the brush holder we mentioned earlier. Next subsystem is the outer shell. So the outer shell has several standard components. The first one is the key lock combination we found on McMaster-Carr. The second one is a door handle. We also found this on McMaster-Carr. The third one is a drop-in nut with spring attached. This is used to attach the various panel, the outer panel that protects our inner frame. The last one is the door hinge, also from McMaster-Carr. The only custom design components for the outer shell will be the panels, and we consider these possible materials from metals to acrylics or even plywoods. So here are the 7 criteria we considered. And in the end, we settled on 316 stainless steel, which is a level higher than the 304 stainless steel we use for the interior components, because the exterior shell might encounter some rain, so we figured that giving it extra protection to corrosive might be a better choice.
So our storage system consisted of bins that can be moved in and out of the sorter. All components of the storage bins were custom designed in order to maximize the space in the sorting machine. The first component is the base of the bin. The bin must be able to support the weight of the plastics as well as the impact of the plastics as they fall into the bin, and they also must be weather resistant. Some potential materials include various forms of plastic, steel, and wood. These are the various aspects we considered for choosing our material for the base of the plastic bin. So after going through the material selection process, we ended up choosing high density polyethylene as it has high impact resistance and it is weather resistant as required. The next component is the wheels of the bin. The wheels must withstand the loads carried in the container, as well as be weather resistant. Potential materials include rubber, polyurethane, polypropylene, and nylon. This is the material selection process we went through to pick the material of the wheel. At the end, we chose rubber as the material for the wheel as it has a strong grip, is weather resistant, and is relatively cheap. The next component is the axle for the wheels. This provides a support for the wheels to turn about. The axle must be impact resistant and weather resistant. Potential materials include galvanized steel, stainless steel, nylon, and polyethylene. This is our material selection process. We end up choosing galvanized steel because it is weather resistant and impact resistant. And the picture there is the picture of the assembled bin.
All right, now we're going to go over the human factors. There are three main user-product interactions. The first being inserting plastic into the plastic sorter. Second, removing the plastic from the sorter, and maintenance work. So let's examine inserting the plastic interaction for this task analysis. It starts with grasping the handle and then pulling the handle till the door is all the way open. Following these steps, the user will place the plastic on the open door, grasp the handle, and then close the door. We used a rapid upper limb assessment tool in conjunction with Simmons Jack software to validate the location of the handle on the door. This concerns the first step of the task analysis for inserting the plastic, grasping the handle when the door is closed. It is important to note in the Jack software, the virtual testing was conducted with a male figure in the 50th percentile in height. So this first one is the preliminary handle location, is scored a 3, with a body group A scoring a 4 and body group B scoring a 2. Body group A is the posture for upper arm, lower arm, wrist, and wrist twist, while body group B is the neck and trunk. So if we look at moving the handle 5 centimeters lower, it affected the score by bringing it up to a 4, while body group A scored a 5 and body group B scored a 2. When we moved it 5 centimeters higher from the preliminary location, it also scored a 4, with body group A scoring a 5 and body group B scoring a 1. So this is the rubric for the assessment. All handle locations fell in action level 2, meaning low risk for the user. The original location had the lowest assessment score, so the height was verified to 1.3 meters high. There is some error with the Jack software virtual testing. As a result, real-life testing would be recommended to finalize the handle location.
So now we're going to go over the DFMEA analysis for our product. The failure mode with the highest risk priority number in the conveyor belt was the motor failure. The motor is the driving force that powers the pulleys located in the belt. And if it were to fail in any way, it would cause complete shutdown of the whole belt system. What makes it so risky is it is not easily detectable compared to some others, and its severity is moderately high if it were to fail.
In the sensor ring, the failure mode with the highest RPN is a sensor failure. This is when a sensor is not calibrated correctly or the image processing fails or for some other reason the sensor fails to identify the material. This failure has a low likelihood of happening, but it would be very severe and hard to determine if it occurs.
In the singulator, the failure mode with the highest RPN is a failure mode where two or more pieces of plastic do not become separated, possibly because they ended up stacked on top of each other. This would potentially impact the purity of the sorted plastics, as both would be sorted into one bin. The controls for this involve manipulating the singulator speed to ensure that all plastics are separated as effectively as possible.
Much like the conveyor belt, the failure mode with the highest risk priority number is the motor failure. The motor is the driving force that dictates the speed and force of the paddle as they sort the materials. If it were to fail, there will be nothing to monitor the sorting of the plastic, and all the materials will just collect in a final bin.
The next section is sustainability. with regard to social design considerations. We aim to address these by encouraging recycling in communities, making hassle-free, and adapt to current recycling infrastructure.
For economic design considerations, we mostly focused on incentivizing recycling by not making it a tedious task for individuals, which allowed us to reduce strain on the companies.
Lastly, we address some environmental design considerations, such as using renewable materials, no thermosets, glue, or any harmful substance, auto power saving when no plastic is detected, and efficient power consumption.